Welcome back to the deep dive. We're here to cut through the noise and really get to the heart of things. Today, we're tackling a big one, neural networks. You've probably seen the term everywhere, maybe glanced at some, well, pretty dense academic papers, complex equations, and maybe felt like, wow, this is just totally impenetrable for a regular developer. Our mission today, to pull back that curtain, we want to show you that actually at their core, these things are built on programming concepts you probably already know and use.
Exactly right. The goal here is demystification, pure and simple. We want you to walk away from this deep dive seeing that these, incredibly powerful tools are basically put together from ideas you're already familiar with. We're talking functions, loops, maybe some object-oriented thinking, data transformations, the stuff you work with. Think of it like this. A neural network is basically just a giant flexible function.
Yeah.
But here's the cool part. It learns to write its own rules based on the data you feed it.
Okay, and we're going to take this step by step. No jargon overload, promise. We'll use analogies. Keep it grounded in developer terms so you really get it. So let's start right at the beginning, strip it all down. What is a neural network at its most fundamental level?
Okay, at its most basic, a neural network is really quite similar to a function, like one you'd write in Python or JavaScript. Takes some input, does a bunch of calculations inside, and spits out an output. Standard stuff. But here's the twist, the really crucial part. Instead of you sitting there writing every single if-else condition, every specific formula, the network's internal bits, its parameters, we call them weights and biases, they get tuned automatically. How? By looking at tons of data. It keeps adjusting itself until that function reliably gives you the outputs you're looking for. It's a real paradigm shift, actually. Think about traditional software. Usually it's a stuffware. You define the rules, you give it some input, boom, you get output. With neural networks, it's flipped. You provide the data, you provide the desired output for that data, and the network figures out the rules itself. It learns them.
That is a pretty fundamental shift in thinking. Okay, let's make that concrete. How about a spam filter? The old way, right? You'd write rules like, okay, if the subject line has free money, flag it.
Wow.
Or maybe count the exclamation points. If there are more than 5, it's probably spam. You're coding explicit logic.
Right, and spammers get clever. They change tactics. So you're constantly playing catch-up, updating those rules manually. It's endless.
Exactly. And the internet just moves way too fast for that. You can't keep up writing static rules. So the neural network way is different. You just feed it like thousands and thousands of emails. Some you've already labeled spam, others you've labeled not spam.
And from all that data, the network starts to pick up on the patterns, the subtle things, maybe weird combinations of words or odd formatting. Things a human might miss or find hard to define in a rule. It learns what spamminess looks like statistically, which means it can often spot new types of spam it's never seen before just because they share underlying patterns.
Ah, okay. So it's like you hired a super focused assistant.
Yeah, kind of. Imagine hiring a junior dev, but instead of writing code, their job is just to read all the existing code and data logs nonstop and just figure out the hidden connections. Except this dev works entirely with numbers and statistics, finding those correlations to build its own internal logic.
That analogy helps. Okay, but then there's the whole neuron thing. People talk about neurons. Is that literal? Like, are we simulating brain cells here, or is it just a name?
Yeah, good question. It's best to maybe forget the direct biology comparison for a minute. It's mostly an analogy that's stuck. In a neural network, a neuron is really just a simple mathematical unit, a tiny calculation. Think of it as a small formula. Output, activation, weighted some inputs.
That's basically it.
Okay, break that down. Output, activation, weighted some inputs. What are those pieces?
Right, so the inputs, just numbers coming in from whatever came before, maybe the raw data, or the output of other neurons in a previous step. The weights are crucial. They're just numbers too, but each input gets its own weight. It basically tells the neuron how important that specific input is, like a knob you can turn up or down. Then there's the bias. It's just a single extra number that gets added in. It gives the neuron a bit more flexibility, like letting it activate even if all the weighted inputs happen to be 0. Think of it as baseline activation level. And finally, the activation function. This is super important. It applies a transformation to the result of the weighted sum plus bias. Usually, this function is nonlinear.
Nonlinear. Why is that important?
Because if everything was just linear, simple additions and multiplications, the whole network, no matter how many layers you stack, could only ever represent linear relationships. It would be like trying to model the whole world using only straight lines. Real-world data is messy, curvy, complex. Nonlinearity lets the network learn much more intricate patterns. It allows it to bend and warp its decision boundaries, so to speak.
Got it. So if I'm thinking like a developer, That formula, output, activation, weighted some inputs, it looks really familiar. Like I could code that up pretty easily.
Exactly. You absolutely could. If you picture it in Python, it's straightforward. Def neuron, inputs, weights, bias, hashtag calculate the weighted sum, total, dot product, inputs, weights, plus bias, hashtag apply the nonlinear activation, return activation function, total.
Right, you need a dot product function and pick an activation function, but the structure is simple.
That's really all a single neuron is. It's just this little calculator taking numbers, multiplying, adding, applying one final function. No magic brain simulation needed.
Okay, so that's one neuron, one little calculator. How do we get from that to a full network?
Simple. You just take a bunch of these neurons and put them side by side, running in parallel. That group of neurons is called a layer.
A layer, okay.
And then you just stack these layers one after another. The output of one layer becomes the input for the next layer. Stack enough layers, and you've got yourself a neural network.
And when people say deep learning,
That just means you stacked many layers. Deep refers to the depth, the number of layers in the stack. That's it.
so we have neurons making layers, layers stacked up. But how does stacking them actually achieve anything complex? Like, how does it go from simple calculations to recognizing a cat in a photo?
That's where the power of composition comes in. Think of it like nested function calls, maybe.
Mm-hmm.
Each layer takes the output of the previous one and performs its own transformation on the data. But these transformations build on each other. They create a hierarchy of features. Yeah. So imagine you're feeding an image into the network. The very first layer might learn to detect really simple things like basic edges, corners, maybe simple gradients of color, very low-level stuff. The next layer takes those edge detections as input and learns to combine them into slightly more complex shapes, maybe simple curves, circles, basic textures. Then the layer after that might combine those shapes to recognize parts of objects, an eye, an ear, a patch of fur. And finally, the later layers put all those recognized parts together and say, okay, I see eyes, ears, fur, whiskers arranged in this specific way. Aha, that's a cat. Each layer learns increasingly abstract representations based on the output of the layer before it.
That makes a lot of sense. It's like building blocks. It reminds me a bit of using pipes on the command line in Linux or Mac OS.
That's a great analogy.
You know, like some oglog file grep error, so unique. Each command does one specific, relatively simple thing.
Right. grep finds lines, sort orders them, unique removes duplicates.
But when you chain them together with pipes, you can achieve something quite sophisticated. The output of one becomes the input for the next.
That's almost exactly the principle behind layers in a deep neural network. Each layer does its own transformation, and the real power comes from composing those transformations sequentially.
Okay, I think I'm getting the structure. Neurons, layers, stacking them up for hierarchical feature learning. But we still need to tackle the learning part. How does this whole giant function actually learn? How does it write itself, as you said earlier? What's the mechanism?
Right, the learning process, that's called training. It's an iterative cycle, and it usually involves these four main steps, repeated over and over. First, you do a forward pass. You take a piece of training data, say, an image of a cat, and feed it into the network's input layer. It flows through all the layers, each doing its calculation, until the final layer produces an output. Maybe the network guesses dog initially.
Okay, so it makes a guess. Step one.
Step 2, calculate the loss. You compare the network's output, dog, with the actual correct answer, cat. You use a mathematical function, the loss function, to measure how wrong the network was. It spits out a number representing the error. Higher number means more wrong.
Got it. Measure the error. Step 2.
Step 3. This is the clever bit, the backward pass, or backpropagation. The network essentially works backward from that error value. It uses calculus, specifically the chain rule, to figure out how much each individual weight and bias in every single neuron across all layers contributed to that final error.
Whoa, okay, so it assigns blame, basically.
Pretty much. It calculates the gradient, which tells you which direction to adjust each weight and bias to reduce the error. It figures out, okay, if I tweak this weight up a tiny bit and that bias down a tiny bit, the overall error should decrease.
Fascinating. Assign blame and figure out how to fix it. Step 3.
And finally, step 4, weight update. You actually make those small adjustments. You nudge each weight and bias slightly in the direction calculated during the backward pass. You usually use an algorithm called an optimizer to manage how big these nudges are.
Ah, the optimizer you mentioned earlier. Tell me more about those. How do they work? SGD and Adam, you said.
Right. Optimizers are algorithms that guide that weight update process. Think of stochastic gradient descent, SGD. Imagine you're on a mountainside in thick fog. You want to get to the bottom, the point of lowest error. You can't see the whole landscape, but you can feel the slope right where you're standing. So you take a small step downhill in the steepest direction you can feel. That's SGD. It looks at the gradient calculated from a small, random batch of data, that's the stochastic part, and takes a step. It's simple, but can sometimes be slow or get stuck in local minima small valleys that aren't the deepest one.
Okay, simple steps in the fog. What about Adam?
Adam is often more effective. Think of Adam as a smarter hiker. It doesn't just look at the current slope, the gradient. It also keeps track of momentum, like, have I been heading consistently downhill in this direction? It remembers past gradients. And it also adapts the step size for each weight individually. If a weight's gradient is consistently pointing the same way, it might take bigger steps for that weight. If the gradient is noisy and jumping around, it'll take smaller, more cautious steps. This often helps it converge faster and more reliably than basic SGD.
So Adam has memory and adapts its stride. Makes sense.
Exactly. And this whole four-step process, forward pass, calculate loss, backward pass, update weights, you just repeat it over and over, thousands, maybe millions of times, with different batches of training data each time. With each cycle, the network's weights get slightly better, the error goes down, and it gradually becomes really good at the task, whether that's recognizing cats, translating languages, or whatever you trained it for.
It's like, okay, for developers listening, imagine you wrote a complex program. And every time a unit test failed, the program could automatically analyze why it failed and tweak some internal configuration values, not rewrite the code, but adjust some settings to make it pass next time.
That's a fantastic analogy. That's very much the spirit of it. The network is essentially auto-refactoring its internal parameters based on performance feedback.
So it's this constant feedback loop, this automated tweaking process.
Precisely. Or, here's another way to think about it. Imagine all the weights and biases are like settings in a giant .env configuration file for your application. When you start training, all those settings are just random numbers. Your app doesn't work correctly. Training is like running automated tests, the forward pass and loss calculation, logging the failures, the error, and then having an automated script, backpropagation and the optimizer, that carefully adjusts those config values based on the logs. After millions of iterations of test log tweak, the config file is perfectly tuned and your application runs exactly how you want it to. Training is just automated config tuning at a massive scale.
Wow, okay, those analogies really click. It makes the whole process feel much less like black magic and more like extreme automation.
Wow.
So we understand the structure, we understand how it learns. Let's talk about the why. Why go through all this? What makes neural networks so powerful? Why are they basically everywhere now?
The core reason, the big why, comes back to that nonlinearity we talked about. Remember how stacking linear operations just gives you another linear operation? Well, by stacking layers with nonlinear activation functions, something amazing happens. These networks gain the ability to approximate any continuous function, theoretically, given enough neurons and layers. They can model incredibly complex, wiggly, nonlinear relationships between inputs and outputs.
So they can handle the messiness of the real world.
Exactly. Think about identifying faces in photos. The relationship between pixel values and the identity of a person is unbelievably complex and nonlinear. Or understanding human language grammar, context, sarcasm is deeply nonlinear. Traditional algorithms often struggle with this level of complexity because they rely on simpler assumptions. Neural networks, by stacking these nonlinear layers, can learn these intricate patterns directly from data. They essentially learn to draw incredibly complex decision boundaries in high-dimensional space.
And that's why they're behind so many cutting-edge applications we see today.
Precisely. That ability to approximate complex functions and learn hierarchical features from raw data is why they power things like
Image recognition on your phone, right? Tagging photos automatically.
and speech-to-text systems, like when you talk to your voice assistant.
Self-driving cars, understanding the environment around them.
Definitely. And, of course, the big one everyone talks about now, large language models like ChatGPT. Understanding and generating human-like text relies heavily on these principles.
It's incredible how widespread it's become.
And it's worth remembering, under the hood, a lot of the heavy lifting still boils down to very efficient matrix multiplications, multiplying large arrays of numbers, plus those nonlinear activation functions. This is key because we have specialized hardware, like GPUs, graphics processing units, that are incredibly good at doing matrix math in parallel very, very quickly. That hardware acceleration is what makes training these huge networks practical.
Right, so the math isn't just theoretical, it's what makes it work fast enough on modern computers. Okay, so there's clearly a lot of math, even if it's often handled by libraries. Which brings up a practical point for our listeners. Is building and using a neural network something a typical software developer can actually do, or is it still mainly the domain of PhD researchers?
Oh, absolutely. A developer can definitely do this now.
Hmm.
It's become remarkably accessible. You don't need a PhD in math anymore, not by a long shot. The frameworks we have today, like TensorFlow, PyTorch, Keras, they abstract away almost all the really hardcore calculus and linear algebra. You can define a pretty sophisticated neural network in, say, PyTorch, often in fewer than 15 or 20 lines of Python code. And honestly, it looks a lot like defining a regular class in object-oriented programming. You define the layers in the init method and how data flows through them in the forward method. It feels quite natural if you're used to OOP.
That's really reassuring. So you don't need to implement backpropagation yourself from scratch.
Heavens no, please don't. Think of these frameworks as your standard libraries for AI. Just like you wouldn't rewrite a web server from scratch every time, you use libraries like Flask or Express. For neural networks, you use TensorFlow or PyTorch. As a developer, the key is to think of these networks not as some alien mathematical construct, but as another powerful tool, another library providing a high-level abstraction. Your job becomes understanding the concepts, how to structure the network for your problem, how to prepare the data, and how to interpret the results, not deriving the gradients by hand.
Okay, great. So it's accessible. But with all this power and, well, hype, there must be some common pitfalls or misunderstandings. What are some key misconceptions people have about neural networks that we should clear up?
Yes, definitely important to address those. Misconception number one, neural networks are magic. They're not. There's sophisticated math and statistical pattern matching operating on large amounts of data. They find correlations, sometimes incredibly complex ones, but they don't possess true understanding or consciousness.
Okay, not magic. Got it.
Misconception number two, more layers or more neurons always means better results. Nope, bigger isn't always better. Very deep or wide networks can be much harder to train, they need vastly more data, they take longer, cost more compute, and they're often more prone to overfitting.
Overfitting?
Yeah, that's when the network learns the training data too well, including its noise and quirks. It gets great results on the data it saw during training, but performs poorly on new, unseen data because it didn't learn the general patterns, just memorized the examples.
Right, like learning the answers to the test, but not the actual subject.
Exactly. Misconception three, they understand like humans.
Hmm.
As I said, they're amazing pattern recognizers, but they lack common sense, real-world grounding, and true causal reasoning. They learn statistical associations, which can be powerful, but it's not the same as human cognition.
That's a crucial distinction. Anything else?
Yeah, a big one. Always use a neural network. Sometimes a much simpler model, maybe a linear regression, a decision tree, even just some well-crafted regular expressions might be faster, easier to interpret, require less data, and be totally sufficient for the job. Knowing when not to reach for the deep learning hammer is just as important as knowing how to use it. Don't use a neural network just because it's trendy if a simpler solution works well.
Choose the right tool for the job. Classic engineering advice.
Always.
Okay, so let's try to synthesize all of this. For the developer listening right now, what's the key mental model they should walk away with? How should they think about neural networks going forward?
All right, here's my condensed mental model for developers. 1. Think of a neural network as a function that learns to write itself based on data examples. 2. Think of training as iterative refinement guided by errors, like large-scale automated unit testing where failures drive improvements. 3. See the weights and biases simply as mutable state or configuration parameters that get tuned over time through optimization. 4. Treat frameworks like TensorFlow, PyTorch, and Keras as your standard libraries for this domain. Leverage them, don't reinvent the low-level stuff. Focus on the architecture, the data, and the problem you're solving.
That's a really clear, actionable way to think about it. Fantastic. Well, this has been an amazing deep dive. We started with this potentially intimidating topic full of jargon, and I really feel like we've broken it down. We've shown how it connects back to core programming ideas, functions, data flow, iteration, configuration. Hopefully for everyone listening, neural networks feel less like some mystical black box and more like a powerful, understandable tool built on principles you already grasp. You really do have the developer mindset needed to engage with this stuff.
Absolutely. And maybe just one final thought to leave you with, something to chew on. If these powerful neural networks fundamentally operate by discovering and exploiting statistical patterns in vast amounts of data, what is it really that differentiates genuine human understanding, creativity, or intuition from just extremely sophisticated, scaled-up pattern recognition? And thinking about that difference, how might that understanding shape where AI goes next? Will this just be about building bigger and bigger pattern matchers, or is there something fundamentally different needed for the next leap? Something to ponder.